Welcome, and thanks for joining. I'm going to talk today about some of the interesting observations I've made over the last 10 years building models for predictive applications. And towards the end, talk about a very interesting phenomena, how models can induce biases just by themselves, even though the training set was originally unbiased. But to get there, we'll need to talk about a couple of details beforehand that I hope you find as interesting as I did. So with that, talking about predictability and how it relates to possible biases from predictive models and machine learning. So I work as the chief scientist at Distillery, and I'll talk a little bit about what I do for a living, but let's jump right in. The whole point of building predictive models is to have them find these nuggets of sometimes correlation, sometimes causation that help us predict things. But they're quite lazy on occasion, and they are looking for what is the easiest to predict. Let me explain to you what I mean by that. So what does it even mean that something is predictable and how predictable it is? And it's really a spectrum between things where you almost cannot predict anything and things that are nearly deterministic. To give you an example, one of the things that we know are very, very hard to predict are stock markets. So if you are predicting stock returns, if you get more than 60% right, you wouldn't be listening here. You're probably enjoying a sunny day on a private island in the middle of nowhere somewhere. On the other end of the spectrum, we have things like, for instance, telling that this is a cat. So there has been a lot of recent progress with deep learning around these types of visual recognition, where any 3-year-old really can tell that this is a cat. Along those spectrum, what I've been focusing on most is really this middle area of human behavior. Now, even for the things we do, some parts of us are easier to predict than others. There was a very interesting study on Facebook data, for instance, that shows that things like sexual orientation or religion are quite easy to predict once you know enough about me, the things I like, and so on. On the other hand, I have no idea if I will have pizza for dinner tonight. I mean, that depends how hungry my son is. So I can't even foresee my own future, let alone any model predict this with any degree of certainty. Now, let me show you what happens on this spectrum. And let's start with a very simple kind of task here. And let's try to predict who is male. This is one of these Facebook data sets that was publicly available. And what you see here is basically these anonymized IDs. That's the long number on the left. And in the next column, you have a gender indicator that is 1 for men and 0 for women. And we have about 40% men in this initial data set. We also have some years in there, and they are basically the birthdays as provided by the members of Facebook. So in this problem, we also have, and that's what the data on the right side is, all of the likes. And again, they're anonymized, so I don't know what they are, but they all represent certain objects or websites that people have tagged as likes. And I will use logistic regression on sparse data, but it doesn't really matter. You can use that. You can do that with any model class you want. In the first try, what we're going to do, we will try to predict gender purely based on age. You can think about this, where it would fall on the spectrum, but this is pretty much hopeless because your gender shouldn't depend on age, right? Now, it depends a little bit on age because there is some correlation. So the first model here has an accuracy of about 60%, but what I want you to focus on is the histogram in the middle. And this is now a histogram of the predicted probabilities of being male given your age. And you see that the model has some distribution there. What we really care about, however, when we do targeting and in many of the other use cases of predictive modeling for recommendations, for instance, you really only care about one side, like the highest predictions or the lowest. So if we are trying to reach men on Facebook, we really only want these top 1%. And in that group, the accuracy is actually pretty decent. We get 75% males in that group. Now, let us add to the original very simplistic model a lot more data. And in particular, we're going to add all of the likes. This is almost a replication of that Facebook study that we had. What you see now is how different the model behaves. In particular, the distribution of those predictions has become almost bimodal. There are a lot of people where the model knows that they are not male, and there are a lot of people where the model is absolutely certain. So in the top 1% of all predictions, you now only get males. There's also the little part in the middle that I have a circle around. And it turns out, those are people, it's not that the model doesn't know what the gender is, but simply they had no likes. And we are back to only looking at age. It's really interesting to observe the progression when you start on the left top with only age, and then you add in the next image the 10 most common things that people like. So not the most predictive, just the things most people liked. And already then, with just 10 additional features, you get 86% correct in the highest predictions. And so progresses with 100 things that people could like, you get 100% correct. And finally, you find yourself all the way in the right with this very extreme kind of bimodal distribution in the predicted probabilities. This is what I mean by models looking for the signal, and when they find it, they kind of focus in on that, because often it's not a consistent kind of structure, but you have people with more likes and people with less. What I've seen in many applications is that what you really have is a combination that part of your problem are almost random. For some people, you can't predict the gender. And for others, it's really easy. Let me show you an application now for my day job where this becomes really, really important. So what this shows here is over a period of 2 weeks, we saw a huge improvement in our model performance. And this is predicting all kinds of things. People are signing up for credit cards, ordering pizza. So this is across many different models. In an advertising context, we saw this improvement. And I have a hard time believing that over about 2 weeks, all of a sudden people became so much more predictable. So it's not the death of free will. So I have to tell you a little bit more what exactly we are predicting and what data we have for that. Our company, Distillery, works in the advertising technology space. And so we have anonymized browsing histories. So we know for a large number of devices, kind of a time series of the URLs that they have visited. So here you see some of them. And then when we work with an advertiser like Azure of Microsoft, we are trying to see how all of the other things that people do can help us predict who's actually in the market for Azure. This is a kind of brief view into what's under the hood of the system, where you basically here get a glimpse at this logistic regression model. And what I have highlighted in the circle here is currently the model has 360,000 non-zero parameters. So that's not your run-of-the-mill logistic regression model. And the way these are estimated, you have some details here on the right, like using stochastic gradient descent and a lot of penalties in the process. Now, with this context now, what happened to this system that all of a sudden we get so much better predictions for things like predicting who will sign up for Azure? When we started looking under the hood and see like what are the most predictable features, we saw something really weird. For instance, this website called Women's Health Base. Apparently, if you believe the models, a person who looked at Women's Health Base and read some articles there was then very likely to show interest in hotels, pizza, credit cards, Microsoft Office, and even luxury cars. This is odd because there's no contextual relationship here, right? I mean, maybe in medicine, but why luxury cars? And it wasn't just women's health based, but we found a number of URLs that no matter what the thing is that we're trying to predict, they showed up as being really indicative of a person then going to that brand's homepage and showing interest in products. Now, there was one thing that all of these websites had in common. And to show you this, let's take a view at what cookies do consecutively. So we're looking here at an overlap, meaning what do people visit together? And we have this data because we are working in this programmatic advertising space where we are buying the opportunity to show ads based on bid requests. And these come, for instance, from websites loading with small areas for ads being available. And then as the website loads, they're sold in real time. Our company is at the receiving end of that stream. And so we're getting about 100 billion events every day. Now let's look at what the world of this kind of overlap looks like. This here is a view from 2012. And what you see here is a little structure. So let's look a little bit closer on what this may mean. And it turns out that this is the Boston Herald. There's a lot of information about Boston, and it makes sense that people who try to maybe plan a trip or live in Boston kind of look at all of these sites. So therefore, an overlap of 50% of people visiting all of them makes kind of sense. Now, what's going on in these very, very dense parts of the graph? If you zoom in, you actually see women's health space right there. But aside from the fact that it has so many other websites it's connected to, I mean, people must spend a lot of time on the internet here, you also see really unrelated other stuff with very obscure spelling, like wrestling news and documentary, China on TV, and so on. So as far as I'm concerned, there's no way that this is human behavior. I can't imagine anybody doing this. So how is this related to our models getting so much more predictable over this time period when we observe that? What actually happened that explained this phenomenon in our world is the rise of the machines. It is a new form of advertising fraud, meaning these are not people, obviously, but some of them are bots. We have seen a huge increase of this, what we call non-human traffic on the internet. It was around 6% in 2011, and to this day, I think we're still north of 30%. Now, the fact that there are bots out there, why does it make my problem so much more predictable? The reason is, and that's what actually happened in these 2 weeks, there's a new generation of bots that realize that you earn a lot more money if you make these fake traffic also visit very kind of rich brands that spend a lot of money on advertising. So here's the business model. You create a fake website, let's say women's health space, and then you hire somebody who writes a bot that keeps visiting your website. And every time one of these bots visits your website, you then sell the ads on that website to companies like Distillery. We will probably not bid very high on those unless these bots also start visiting the exact sites that we're trying to predict. And so to make the business model a lot more lucrative, all the bot owner had to do, it's called cookie stuffing, meaning pretend to be more human, and in particular, do all these things that marketers want you to do, clicking on ads, going to websites. The problem is that now some of these events I'm trying to predict are actually done by people, and others are done by these bots. And to see how pervasive this issue is, here is our measurement on the bot traffic for a number of these conversion events that advertising is trying to optimize to. And for instance, you see the worst offender by far are things like video completion. meaning somebody's measuring whether you skip the video ad or you actually sit all the way to the end. And of course, only bots are patient enough to wait all the way to the end. Now, bringing this back here, we have really a mixture of two different populations, people and bots. And coming back to my framework, it turns out that it's much harder to predict what people do, because after all, we have some free will, and it's hard to find out who really is in the market for certain products. Whereas it's pretty easy to detect that this is a bot whose sole purpose was to take actions that ultimately give them benefit for the advertiser. So if you put this now back into that distribution, what we see is that humans make that midfield that's very hard to predict, whereas the machine can very easily predict with high certainty that a bot will take a certain action. And if you now use this technology to target people, well, you actually don't target people. The only thing you end up targeting are these bots. Once we had a bot detection in place, my performance went back down. And for once, that was actually a good thing. So we were quite happy to see that progression. What about clicks? It turns out there's almost no problem where this doesn't happen. In advertising, clicking is considered an indication of interest in the product, consumer intent. But the reality is that clicks have also their share of fraud, and I think more interestingly, also accidents. So I'm not sure about you. I'm not aware that I click on ads unless all of a sudden something opens up on my screen and I realize that I probably accidentally clicked on it. Now, it turns out that these accidental clicks are easier to predict by a machine learning algorithm than the intentional ones. So the same mechanism here will lead to the accidental ones getting higher scores. And then if you target the most likely, you will only get the most likely accidental ones. And evidence for this is an analysis we did for some mobile advertisers. We consistently see the highest click-through rates on ads in mobile on certain apps. And to a large extent, these are games, but you also see things like the flashlight app very consistently. No matter what it is that you're trying to advertise, people click at a very high rate on those ads if shown on the flashlight app, where it's really just people fumbling in the dark. So the model really only learned the context in which accidents are more likely to happen. And this is almost the irony, because before you used machine learning and you just used the click-through rate as a metric without all that rich information, the accidental clicks didn't really matter that much, because as long as the right kind of target group, let's say men in this case, have a higher intentional click rate, you could actually correctly conclude from this picture that this is where you should spend your advertising money. But that, unfortunately, today doesn't work anymore. And before you had machine learning and big data, your conclusions about who to target were right. But now that you have machine learning, because it focuses on these easy contextual ones, it no longer reaches the right people. Let me show you another example. And here we are trying to find good audiences for to advertise luxury cars. Well, if clicking on ads isn't a good thing to optimize towards, and maybe visiting the Mercedes homepage isn't really that good either, assuming that there are some bots there, how about we're trying to predict who actually physically goes to a dealership? Well, if this is a machine learning problem, you need a training set, meaning you also need labeled data. How would I even know that somebody went to a car dealership? So now I have to come clean about the full kind of extent of our data. And I don't just have browsing histories, what people did on their kind of on the internet, but we also see a lot of data from mobile devices. And whenever there's an ad shown on a mobile device, in the bid request that we get when we ask whether we want to actually show an ad, often it brings along the lat long that you're currently located at. Now, the location data is not very clean, so I never know with certainty. So that's what the question mark means. These location data is known to be very, very noisy. But how can I tie that location data on your mobile device back to the things that you do online on your laptop? So in the middle here, based on the IP address, we can associate devices that show up in the evening on the same Wi-Fi. So you can identify certain IP addresses to be likely home Wi-Fis. And so that way, we can now build models that use the browsing history of your laptop to predict whether or not your mobile phone will go to a car dealership. So what does that mean? You really have now 3 different possibilities. In your training set, some of the people actually were at the dealership and you got the correct history. Some of the people actually didn't really go to the car dealership, but were sitting maybe in a coffee shop across the street, and the uncertainty about the location just makes it look as if you were at the dealership. And finally, you may have people who hacked into your Wi-Fi. So yes, you have been at the dealership, but the browsing history I have as my features weren't yours, but then the ones of your neighbor. So let's look at the model here. This is again a logistic regression with hundreds of thousands of features. And here are the most indicative URLs, meaning if a person on their laptop looked at any of those, they were also very likely then in the near future to show up with their mobile phone at the car dealership. Let's look at this in more detail. So here, first off, you really see a lot of evidence that they're researching cars. And not just Mercedes, but also kind of other consideration brands, Acura and Toyota. What you also find is real estate sites. So there seems to be some truth to this notion that marketers have that when people buy houses, then they buy all kinds of other things, including new cars. And finally, we have a couple of fitness websites in here. I think that's a life stage thing. So there's a certain person who actually starts picking up sports again in conjunction with buying a car. But if you look at this, this is actually surprisingly good. Given all the problems I said the data set may have had, how comes that this time the model really seems to find the right people, meaning people who are in the market for cars? So let's ask the opposite question. How much randomness can a model absorb? And when I mean absorb, I'm saying that I know that some of my labels are wrong, and I'm now going to pretend that some of my labels are wrong. So I'm on purpose changing labels in this new data set, but in the test set, I know the truth. And the very surprising result is that with this kind of random changes to the dependent variable, even if only 50% of your labels came from the original, you still have more than 95% correct, meaning 95% of the highest predictions are indeed male. And the distribution here shows that while the model gets confused, clearly in the middle, you see this flattening out, but the peaks on the outside still remain quite strong. So the surprise here is that a model can absorb a lot of random noise. In fact, I may feel more confident about the predicted labels of these very high predictions than the ground truth of my training set that I started with. Let's do another example here, and this is going to find frequent travelers. Frequent travelers, you would assume, go to airports. So let's predict who goes to JFK. And here's the model. Well, what does that stuff mean? We see on the top some Spanish language kind of religious sites. The next layer down, that's much more telling. These are associations of flight attendants. A lot of NFL fans and sports fans in general. And then finally, and my apologies, but that's what the data said. So what happened here? How come the model finds very different people than what you expected? Well, it turns out you didn't really ask the right question. Yes, we are predicting people who are JFK, except that it's much easier to predict people who work there and are consistently showing up at JFK, and the elusive frequent traveler is much more difficult. So again, on this spectrum, with that model, you only find people who work at the airport, not those who travel there. What's the bigger picture? I promised to talk about biases. Well, the bigger picture, if you understand kind of the mechanisms I explained here, is that in all of these applications, and we're now talking about predictive policing, the jobs that you are recommended to on LinkedIn, and even in advertising, I'll talk about Latanya, have this property where the model may just find what is easy. So the case of Latanya Sweeney was that she is a professor at Harvard, and when she Googled her name, in your tenure case, she saw a large number of really concerning ads asking whether she was arrested before, or from a website called mugshots.com. So how can models kind of go off the rails that way? And one explanation is that even if the data set was clean to start with, in these applications, it very well may be that the model finds local pockets of predictability that are not at all what you're interested in. And so looking at the job example, maybe some subpopulation is easier to predict that they will succeed, not more likely. So if your resume or your CV is very kind of streamlined and kind of has a consistency, it is possibly easier to predict that you do well. Whereas if you have breaks or more kind of other things that you did during life, it may make it harder for your model to assert that you will be a good fit. And this is the problem that I looked at in my final analysis here, specifically focusing on gender. One of the things we see, and this is here a predictive task on the Facebook data set, is that while the positives had an equal ratio of male and female, if you look at the top N predictions, so now on the left, these are like the top 1%, top 4%, you see that in the highest predictions where the model was the most certain about the outcome, the percentage of women was much, much lower, only 20%, despite the fact that in the training set, they were 50% of the positives were female. So it is, in fact, possible, and here you see an example where exactly what I outlined happened. It was somehow easier for the model to predict on this particular task that the male subgroup of the training set was taking a certain action versus the female. Across many of these different tasks, you see this diversion. It doesn't have to be always in favor or in disfavor of men or women. So the observation here is that depending on which group is easier, you will get these extremer base rates, meaning very, very small percentage of one sort or very large percentage of one of these subgroups. And this is here an analysis over a number of these tasks that I extracted from the Facebook dataset, where you see under random, you would expect the blue distribution. But when you actually look at the percentage of these subpopulations in the top 10%, you see this much wider tail of clearly biases induced by the model itself. I finally tested the hypothesis that this is indeed related to this notion of predictability by building two models. One only predicting the outcome for female, and another one only predicting the outcome for male. And what you see here is basically the difference of how well these models performed. And you see sometimes that the model for women was a lot better, and sometimes the model for men was a lot better. And the relationship here shows this performance difference on the x-axis in terms of AUC, and on the y-axis, this observation of the gender bias that we observe in the top 1% of predictions. So all this to say, it is not enough when you think about biases of using predictive models for many different applications in terms of the training set. Even if you de-bias your training set, if you make sure that you have an equal percentage of men and women being positive in your training set, you can still, in the highest predictions, the ones that you will see recommendations for, have very notable deviations from that desired 50-50 rate, if this is what you think is fair and equal. And that really means that as you think about the application, it is not enough to think about the training set, but about the translation of what the model predicts to the action you want to take. And if you care about fairness, you need to make sure that your actions are fair, that you will reach out to 50% male and 50% female of those tops that were recommended to you. With that, thank you very much. And I'm not sure if I can take questions on here. So there is a question saying that if the algorithm itself cannot be biased, but the data is, can't we curate the data set that is used? What I'm saying is that even if you curate the first order bias, meaning you make sure that of the people who succeeded in their job, half of them were male, half of them were female, the predictions on that data set that was kind of first order unbiased can be second order biased, because it might be that it's simply easier to predict that women will succeed and men than men. And therefore, the model creates a bias, no matter how diligent you were about curating the data set. Question is, what if there are multiple categories representing parameters of bias? What if there are too many categories to easily break it down? So that was a question by Voxment. I honestly don't have a good answer even for the first one, other than before you kind of mail out resumes, you need to sit back and kind of specify, I want the 5 top male and the 5 top female, or maybe you then have to go and break it further down into all of the other categories of fairness that you want to consider. I don't see an easy answer then. It's your moral decision as human. You can't delegate the moral decision about fairness to an algorithm. If nothing else, that's what the talk really kind of highlights here. We still need to own the decisions that we take based on the recommendations of these algorithms. Rachida asked, can we say that we should check if the features are biased? It's almost, so the first order bias you can check, but the features themselves aren't biased either. They are just kind of jointly more predictable. So yes, you can possibly see if for men the correlation is higher with a single feature, but it's almost like you have to actually build the model to then test it to see whether it happens. Again, to the point, I don't think you can do it before you even build the model. You have to kind of wait and see, because different model classes may find different types of signal. Sometimes you see linear models having very low predictability and a decision tree a very high one. So you actually have to watch this play out and look at the back end when you get the predictions, what happened. But you can, of course, check if you just pick the top 10 predictions and see whether they now are kind of skewed based on the desired distribution that you consider fair. You can check that part on the end. It still doesn't fix your model. And I don't think you can actually fix the model. The model will retain these properties. There's another question of which types of models are most or least susceptible to this bias. I actually think the more biased models are less susceptible to the bias. In terms of simpler model like linear models that have high bias and low variance are less likely to find pockets of predictability than the more complicated ones like decision trees or deep learning, and those. They are more likely to be able to find these kind of very specific terms under which something happens. All right, thank you guys.